So welcome and thanks for showing up that early. So my talk is about content address storage and verified streaming for iroh. And about myself, I've done quite a few things. More recently, I've worked in peer-to-peer networking, trying to build applications there. And I was always a little bit held back by the fact that the fundamentals sometimes don't work as well as they should. But the talk is about content storage and verified streaming for iroh. And iroh is not HTTP. It is not something which I can assume that everybody knows. So I'm going to spend a little bit of time explaining what iroh is in the first place. Okay, so first about our team. So we are a group of grumpy old engineers. Well, this is not quite true. I'm actually the only engineer that is really old. But the others are also quite experienced. For example, that's not their first startup, and they've worked on projects like IPFS, Filecoin. We got somebody who used to work for Google. So this is the general vibe is more like, why can't things just work? It's not like we are going to build the future, like Huli or something in Silicon Valley. It's more like, why can't things just work? Okay, we have to do it, I guess. That's basically the vibe. So we love simple things that work, and in many cases, surprisingly, even the simple things, like just being able to make a connection, are not as flawless as they are in, let's say, in Web 2 networking or in like classic client server. You can rely on the base pretty much. In peer-to-peer networking, that is almost the case, but not quite. And you all know that there's a big difference between something almost working or like working for a demo and something working so well that you can rely on it and just forget about it, basically. It's somewhere deep in your stack and you never have to worry about it. And that's kind of what we're aiming for. We want peer-to-peer networking to be something you just put in your stack, whether you have a peer-to-peer application or just an application that uses peer-to-peer stuff for some aspects. And, well, we decided nobody else is doing this or nobody else is doing it in the quality that we would like to have. So it's up to us. OK, so iroh, this is the long definition. iroh is a library for direct quick connections between nodes identified and encrypted using ED 25519 key pairs. OK, this is quite a long description. It's not very memorable. So I'll just say iroh is quick, but P2P. For those of you that don't know what quick is a new networking standard that is also the underlying transport of HTTP3. So this is not something out of the peer-to-peer world. This is something out of the good old client-server, giant cloud providers world, which we just try to adapt a little bit to make it work for our use case. OK, so what does it mean to be peer-to-peer? This is basically two things. The first thing, we want to be able to dial another node, not by their location, where they currently are, because at the end of the day, we don't really care where they are. We want to dial them by node ID. The node ID is just the public key of the key pair, and this is something that doesn't change over time. Whereas the location of another node, especially in a dynamic environment, might change all the time. So if you want to have a catchphrase for this, it's basically who, not where. I want to know who I'm communicating with, and I don't care where they are. I mean, in fact, I just want the system to look up where they currently are. I'm not interested in this whole thing. And what does that mean? Basically, the old tradition is you have Alice and Bob, and Alice just wants to talk to Bob. Alice is identified by key pair. Bob is identified by key pair. Alice happens to know the public key of Bob. And Alice just wants to talk to Bob. She does not care where Bob is. And this is, unfortunately, this is not how TLS and normal connections work. They this is kind of the state that you have with a quick connection, a traditional quick connection, which is very client-server focused. So Alice wants to talk to Bob, but she cannot talk to Bob at all because he's somewhere else. So she has to talk to Steve, the manager. And so what she has to do is, first, she needs to find out where Steve is. Then she creates a connection to that server. And then, even after, then she's talking to somebody, and then she uses this whole certificate chain to figure out whether it's actually Steve, the manager, she's talking to. So this is not what we want, but it turns out there's a nice new extension to TLS, which is called raw public keys in TLS. And that allows us to encrypt the connection directly by just putting something derived from the private keys into the connection. This is not anything we've came up with. This is just a standard way to use TLS in a somewhat non-default way. Okay, so this is one thing. We want to be able to connect to somebody just by their identity, not by their location. And then the second thing we want direct connections. This is a huge topic, which is, I gave a talk about this last year, so if you are interested in the details how this works, just watch the video from last year. But for now, just assume that we are doing a pretty decent job making it work. So this is the situation. We got Alice and Bob. Imagine Alice is in a hotel in Malaga, Bob is in a conference in Malaga, and currently the state of the art is that they cannot talk at all because they're both behind the NAT and they're not behind the same NAT. So basically each of them has a different private IP address and they cannot talk at all. What they can do, however, is talk to a server, and this is how a lot of communication works these days. Like, for example, they both are in the same, let's say, Slack chat, and that happens to be that they can talk to a server, which then frequently is in US East 1. So just because two people that are both in Malaga want to talk, and they have to communicate with a server in US East 1, just to be able to do that. And that makes me both sad and angry. What iroh allows you to do through something called a relay network and hole punching, the details, watch the other talk, is that they can both get a direct connection to each other. There is a brief phase where they don't have a direct connection, but then they switch to a direct connection, and then they can directly talk. So this is the two things that iroh does to make peer-to-peer quick connections. Okay, now this is kind of a diagram of this is peer-to-peer quick, and below you see all the things that are required for this complex machinery to make the hole punching and the direct connections work, and the encryption by key and so on. And above, you have a large number of use cases. By the way, these are not use cases that you could build on iroh. These are all use cases that people are currently building on iroh. So for everything we have up there, there's actually somebody trying to build this. And you see this has kind of an hourglass shape. So there was an essay on Hacker News a few years ago, which was called "The Internet was built with a narrow waist." So the idea is the internet is pretty complex at the transport level. There's tons of different transports. It's also pretty complex at the application level. There's a huge number of different applications. But there's one thing that everybody has to agree on, which is IP. And this is why the internet is so successful, because you have the complexity below hidden and the complexity above hidden to the transport. And what I'm going to say is basically that peer-to-peer quick is what I consider the most useful narrow waist for the peer-to-peer internet. Because this is something that everybody can agree on. Everybody needs connections. Quick connections have some useful properties like encryption and so on. And so iroh is the first, I mean currently the only, but maybe somebody else is doing it. It's the first open source and open standards implementation of peer-to-peer quick. And that's why I think it's a very important component. So now let's take a quick look. So what do we mean by open source? Everything, really everything is open source, not just the library itself, but also the support infrastructure that you need to run it is open source. So if you want to run your own infrastructure, there's nothing we can do to stop you from doing that. But of course, we would like if you use us, but it's all open source. You can just take it and never talk to us. And then, this is a recent development, we also try to build everything on open standards. So not just the quick connections themselves, but also a lot of the machinery that makes the underlying peer-to-peer quick work we are currently changing that to use either IETF RFCs or in some cases we have to use IETF drafts, and in some other cases we use other well-established standards. But every single component that we can try, we try to make everything based on some kind of established standard. It's not simple. It's not like we're plugging just stuff together. It's pretty complex machinery. Okay, so that is the part about what iroh is. I think you should have a rough idea what this is good for now. Now let's a quick overview of what people are building on it. We got a private chat, file explorer, space drive. We got machine learning, distributed machine learning. We got an app where people can watch a movie together. We got game studios. We got blockchains that are focused for AI agents. So as you can see, it's quite a variety of people that are building on this. Okay, so now we get to the actual topic of the talk, which is iroh-blobs, which is a library for Blake-free verified streaming, which is built on top of iroh. So now, basically, the basic idea, where the idea of iroh is who, not where, here the basic idea is what, not where. I care about what my content is, and I don't care where the content is located. And so what this allows you is to stream from an untrusted source. Let's say you have an untrusted source, like an Ubuntu mirror in Russia, and you got a number of SHA sums, in this case SHA, which give you the expected hashes of all these packets. And then you got another source which says that the SHA-sums file is actually correct. And then you can actually download from this untrusted source. But this has one big downside. It is basically you have to trust, then you download, and then only after you're finished downloading, then you verify whether you actually got the right data. It might be that you get the wrong data and you only notice at the very end. And you might have spent a day downloading this stuff, and then it turns out that it's some random noise. So what Blake-free, a new hash function, allows you to do is basically you verify while you're downloading, and you will, after every 16 kilobyte chunk, you will be able to see whether the data is still correct, and you can abort immediately as soon as somebody sends you a single bit of wrong data. Okay, so now comes the technical part of the talk. Now we're going to learn how Blake-free works. Why Blake-free? Because basically iroh-blobs is just Blake-free with a little bit stuff on top. So Blake-free is a new hash function, a new cryptographic hash function, which is claims to be very fast. It is indeed very fast, we will see. And there are bindings for all languages, and it even works in WASM and so on. Somebody has written a JavaScript application. So it's available everywhere. And now let's see how it works. This is the part where I start walking around. So you start with a file. What you do is you take the file and you split it into chunks of 1 kilobyte. And then you can compute the hash of each of these chunks. And then what you do is you take the hash of each chunk. Every 2 chunks, you put it into something called a hash pair. So this thing is 64 bytes, 32 bytes hash. And you do this until you run to the end, and then you might run out of pairs, so then you might have just one. And then you combine that all the way to the top. And then once you're at the top, you have a single hash pair, and then there's a somewhat special function that takes that and makes the actual hash out of it. And this is basically a construction of a tree hash. You could do this with any other hash function, but Blake-free has the idea of a tree hash baked in, basically. You could also use SHA-256 to hash the individual chunks. That would be slow, but it would still work. So the idea of Blake-free and the idea of a tree hash are not the same. It's just that Blake-free has the idea of the tree hash baked in from the start. And now let's take a quick look why this can be so fast. So this is a modern CPU. As you can see, you have lots of cores. And then even each core has lots of units that can do things at the same time. And the great thing about these chunks is that the computation of every chunk is completely independent of the next one. So what you can do is you can just compute each chunk on a different, basically you use vector instructions to compute the chunks completely in parallel, and these are completely independent calculations, so there's no crosstalk or anything, so you're using the SIMD units perfectly. So this is one way to make things faster. You get a factor of 4 improvement. But we don't just have that, we also have multiple cores. So what you can do is this. You just do groups of chunks on one CPU, depending on how much parallelism your CPU has. And then you do the next group of chunks on the next CPU. So what you end up with is that you actually, for a short time, you're actually using every single thing that your CPU provides. And so you can hash, for example, if you have a M1 Pro, you can hash 64 chunks at the same time, or something like that. And this means that it's extremely fast. Okay, but performance, well, okay, performance is great, but computers are very fast in any case, so you might say, what's so great about this? It's a little bit faster, why should I switch my stuff? Turns out, so this is, by the way, this is how fast it is. I did the demo with a bunch of movies, but then I thought, wait a minute, it's 2025, you have to do something with AI. So what I did is I just took a large AI model, and so 64 gigabytes of DeepSeek R1, and I'm basically computing the hash for all of these functions and also the tree nodes. And as you can see, it's running for a short time. This is 64 gigabytes, and it's done in like 4 seconds. And well, when the animation cycles again, you will see that all the cores are, for a short time, they're all used. So this is one way to actually make a M1 Mac warm, because usually they don't get warm. That's a very nice property. Okay, but like I said, performance is just one thing. Is there something else I can do with this whole tree structure? So it turns out, let's say somebody wants only a part of my data. Somebody just wants a tiny part of my data, but they still want to know that this tiny part actually is the right data for the hash. What I can do then, so the green areas is basically what the other side has requested. I could obviously just send the data, but then the other side would have no way to verify that this is actually the right data. So what I can do is I can basically just take all the nodes from the root to the chunks that I'm sending. And so this is a depth first, left to right traversal. And as you can see, I just go basically down the tree until I hit the chunk. Then I send the chunks. Then I go down the tree again, send the chunks. And then I have a compact representation of just the chunks that contain the area that was asked for, and a bunch of hash pairs. And this thing, this is called the bow encoding, is then sufficient for the other side to prove by redoing the hashing computations that this data is actually part of this giant file which has the hash that the other side already knows. So this is a verified encoding of ranges. In most cases, you will just ask for a single range, but in some cases, it's useful to ask for multiple ranges at the same time in one request. And since it's just a tree traversal, the protocol allows this. So this is the encoding of ranges. But now, if you want to do this encoding of ranges, you don't need just the hash. You need to store the non-leaf tree nodes. You need to store all these nodes up there, because you never know which chunk you might get asked for. So you have to keep them all. So how do you do that? One way would be, what many people would probably do, is just to use a key value store and use some kind of numbering of the tree nodes and then put it into the key value store. But it turns out that it's not very efficient. So what the bow encoding does is you just do a traversal of all these nodes, and you flatten all these nodes into a single file. So in addition to your original file, which you can just leave where it is, you create another file called an outboard, which contains basically the flattened tree, missing the leaf nodes, of course. And that's a very compact representation to get all this data. So you just have a single file, you do some bit flipping, some bit magic, you go into a certain offset and you read the hash pair. And so this is basically what happened when I showed this example. You run this ingestion, and for each file, it doesn't just compute the hash, but it computes the entire outboard, which is basically the entire tree, and writes that into a file. And then once you have that file, you can answer any range request that you might get. And it's way more efficient than a key value store in a database, and you don't have all these database issues like transactions and blah, blah, blah. You just have a file. Files are nice. File systems are good for doing things with files. And you have to use a file system anyway, so you might as well use it directly. Okay, now this is basically how Blake 3 works. So for the normal use case of just computing a hash, and also for the use case of doing verified streaming or verified range requests. Now, the iroh-blobs protocol, as I mentioned, it's just a pretty small layer on top of the Blake 3 and BAO encoding. It's not quite true. We are doing a few things which are an extension of the BAO encoding. For example, in this tree, you notice that there's one 64-byte chunk for every two leaves. So this is an overhead of 1/16. And it turns out this is a little bit much. So what we do is we do something called chunk groups. We group 16 chunks and then only store the tree for 16 chunks. So imagine you have the tree, but you just don't store the lowest layer of the non-leaf nodes. That's basically one improvement that we have. And the other improvement is that we cannot just do range requests, but we can also do multiple ranges. But now let's take a look how the protocol itself works. This is a protocol that runs over iroh connections, but in principle, you could run this over any other connection as well. The basic idea is not bound to iroh. It just happens that we want everything to be peer-to-peer, so we do that. But we'll see that there's also a library which allows you to do this if you just have a normal quick connection or a normal TCP connection. It's just a little bit more work, but you can still do it. Okay, so it's a simple request response protocol. You have a small request, just a description of what I want, and you have a stream which comes back, and this might be a terabyte. If you ask for a large hash, you will get everything. And the response is just the BAO encoding concatenated. So if you ask for multiple things, it will just be one BAO encoding after another. So there's no framing and no flexibility whatsoever in the response. And you might think that request-response protocol is quite limiting, but this is actually not the case because we are dealing with QUIC, so we can have many independent substreams. And that means if we want, we can run 10, 20, 50 of these at the same time, and it will still be efficient. So that's the reason why the protocols itself can be relatively simple in iroh, because you don't have to do any multiplexing. You can just, if you need some kind of stream multiplexing, you can always just delegate this job to QUIC, which does a way better job than if you hack it yourself. Okay, now a few more fun facts about the protocol. So for every request, there's exactly one byte sequence that is the valid response. There's no slack whatsoever in the response. And then if the provider answers and it doesn't have all the data, it can of course stop at some point before you get all the data, and you still might get some benefit from that because at least you might have gotten some chunks. And the protocol is a little bit more complex, but this is basically what the different request types are. So you can say, I've got a hash, give me all the data. That's one request type. Next request type is I've got a hash, and there's a very compact description of how you can specify ranges in case you want to specify many ranges. And basically, the request contains the hash, and then this description of the ranges you want to request. And then what you get back is these ranges. And as we've seen before from the Blake 3 explanation, these ranges always get rounded up to chunks. But this is not a big deal because it's just kilobytes. So if you ask for a single byte, you will always get 1 kilobyte plus a bunch of hashes. But if you ask for a big range, the overhead will be relatively small. And then we have another request where you can ask for multiple hashes, and for each hash you can provide a set of ranges. You might say that this contradicts what I just said, because why would I do the thing in the bottom if I have cheap substreams? Well, it turns out that substreams, streams in Quick, are cheap, but they are not completely free. So imagine you have a situation where you have a lot of tiny content. And then it's quite useful. Let's say you have a bunch of files which are like 10, 20, 50 bytes. And in that case, it's quite useful if you can bunch all this stuff in one request and just do it in one stream. But if you're asking for a bunch of giant files, it almost makes no difference whether you do it as one request or as multiple requests. This is just an optimization for the case where you have small files or small blobs. And then we got a bunch of other requests. This is kind of interesting. Imagine you have a sequence of hashes that the provider already has. And you want to ask the content for that. Now, one thing you could do is you could download the sequence of hashes from the provider, and then you could ask, here are the hashes, can I get the content for them? Well, you could do that, but you would download the data and send it again, so it would be inefficient. Again, it doesn't matter if the size of the data is giant, but if you have a lot of small blobs, which we sometimes have if you have documents or something like that, then this actually matters. So what you can do there is you can say, look, you've got a sequence of hashes on your side, and I want to ask for ranges of this sequence of hashes, but I don't want to actually send you the hashes because you already have them. And this is how it works. Basically, the provider, under this hash, we have a blob, which is a size of a multiple of 32, which contains, again, hashes. And what you can then do, you can send a request. I want, so what this request means, I want self, so this thing, I want this thing entirely. I want nothing of the first child. I want a little bit of the end from the second child, and I want everything from the third child. This is something you would often see if you do a download and the download was interrupted. Like the first part's already done, the second part is half done, and the rest is completely open. This is a bit more complex request, but if you just want to play around with it, you can also just use the two standard requests. Give me the data for a hash, or give me these ranges for a hash. I mean, you can even, we have an example which is a HTTP gateway, which goes to iroh, and then it translates HTTP range requests to these things. Okay, so there's also a corresponding push request for each of these, and this is the end. So the verdict, if you need a hash function, you should really check out Blake 3. If you need verified streaming, you should use bow encoding. If you also care about peer-to-peer, you should use iroh-blobs, or at least check it out. And if you want to try this out today, we have a tool called SendMe, which basically uses this under the hood. And that's it. So, questions?